As a more concrete example, Fedorova speculates that a useful counter to use to detect the thread's CPU-ness versus memory-ness is cycles per instruction. She observes that a memory-bound thread takes a lot of cycles to complete an instruction, therefore it has a high CPI, whereas a CPU-bound thread, it will complete an instruction every cycle or near that, and therefore it will have a CPI of 1 or a low CPI. So then she speculates then it would be useful to gather this kind of information, this counter about the cycles per instruction, and use that as a metric in scheduling threads on hyper-threaded platforms. Given that there isn't exactly a CPI counter on the processors that Fedorova uses in her work, and computing something like 1 over IPC would require software computation, so that wouldn't be acceptable. For that reason, Fedorova uses a simulator that supposedly the CPU does have a CPI counter, and then she looks at whether a scheduler can take that information and make good decisions. Her hope is that if she can demonstrate that CPI is a useful metric, then hardware engineers will add this particular type of counter in future architectures. To explore this question, she simulates a system that has 4 cores where every one of the cores is 4-way multi-threaded. So there's a total of 16 hardware contexts in her experimental testbed. Now she wants to vary the threads that get assigned to these hardware contexts based on their CPI. So she creates a synthetic workload where her threads have a CPI of 1, 6, 11, and 16. Clearly, the threads with a CPI of 1 will be the most CPU intensive, and then the threads with a CPI of 16 will be the most memory-intensive threads. And the overall workload mix has 4 threads of each kind. And then what she wants to evaluate is what is the overall performance when a specific mix of threads gets assigned to each of these 16 hardware contexts. To understand the performance impact of such potentially different scheduling decisions, she uses as a metric the instructions per cycle. Given that the system has 4 cores in total, the maximum IPC that could be achieved is going to be 4. So 4 instructions per cycle will be the best case scenario where every single one of the cores completes 1 instruction in each cycle. And then she conducts several experiments as shown in this figure. In every one of the experiments, she manually and statically changes how the workload is distributed across the cores. So in the first experiment on core 1, the 4 hardware threads will be assigned threads that have software threads that have a CPI of 1, 6, 11, and 16. The 4 hardware threads on core 2 will be assigned software threads or tasks that have CPI of 1, 6, 11, and 16, and so forth. In the first experiment, every one of the cores runs identical mix where each hardware thread runs a task with a different CPI. And then in the last experiment, each of the cores runs a very different kinds of mix where on core 0, all of the tasks are CPU intensive. They have a CPI of 1, whereas on core 3, all of the tasks are memory intensive because they have a CPI of 16. And then the second and the third round of the experiments fall somewhere between these 2 extremes. So what she's trying to do, she's trying to make some static decisions that a scheduler would have made. And in doing that, she's trying to understand whether it even makes sense to build a scheduler that will use CPI as a metric.